Today we'll be discussing about bolted connections too. That is, we have bolts subjected to eccentric shear as well as eccentric tension. Okay. In the previous lab, we had bolted connections subjected to direct shear and direct tension. What did we mean by that? We meant that the shear or the tension, whatever be the kind of force that's being applied, it passes through the centroid of the bolts. Okay. Now it could very well happen in a situation that it is not direct, so we might come across cases where it is eccentric as well. This eccentricity is taken into consideration. That is what we'll be discussing today. So we'll be discussing about um, bolts subjected to eccentric shear as well as eccentric tension. Now let's start off with bolts subjected to eccentric shear. Okay, now take a look at this connection. Okay, you see this is probably a W shape, and we see a plate connected to this. We see two lines of bolts. Okay, and we see that there are two uh, shear forces, two forces in this plane, the plane of the plate. Okay, so that actually acts as shear forces onto these bolts. Okay, now you can see that these forces don't act along the centroid, which means that it is an eccentric shear. You see, this is also shear. You see that Py is a shear force acting, it is a load acting in the y direction and separated by an eccentricity of Ex from the centroid, and Px is a force separated by an eccentricity of Ey. Okay, now this is the view when you look from this side. When you have a look from this side of the column, you see this kind of uh, the plate being is seen here. You don't see Px because it is going out of the plane of the blackboard of the screen. Now in this case, what we do is this is something that we learned in probably CE 203. Okay, suppose we have, I can just draw it here. Suppose you have a load P here, load P separated by ends of E from another point. Now what do? Suppose we need to transfer this load to this point. It becomes what? This load can be transferred directly, but also this load is transformed to this point, and then you need to add a moment to it. The value of that moment is P times E. This is from CE 203. This is what we are doing here. We have two forces, Py and Px. We transfer the Py to the centroid so that it becomes a direct shear, and Px is also transferred. So we have split, we have separated as a direct shear problem here, and then the moment is then acted onto the connection. Okay, onto these bolted bolts. So this this moment is what? Moment is Px times Ey plus Py times Ex. Now these are the design steps. When I'll be going through a problem, then we'll see how this is applied. Now the first step is to identify the weakest plane, then to design the layout of the bolts. We know this from previous lab, and then to determine the capacity of bolt based on the connection that we discussed earlier, whether it's bearing. If it's bearing, you'll have to check both shear as well as bearing capacity of the bolts, and slip critical, we have an equation in the manual. And then we have to estimate the number of bolts. This number of bolts is estimated from this equation, where N equals square root of 6m over Rs, where N is the number of bolts per vertical line. Okay, suppose you have, for example, in this figure, we have two vertical lines. So this equation actually gives you this this n is the number of bolts per vertical line. Okay, equals 6 times moment. This is moment per vertical line. That is, suppose you have a moment of m, the total moment of m, you divide it by the number of vertical lines that you have, vertical lines of bolts. Suppose you have 2, you have to divide this. To get this, you have to divide the whole moment by 2. Suppose you have 4 layers, you have to divide it by 4. In the problem, we'll see in this the problem for eccentric shear, we have the case there are 4 lines of bolts, and then R is the capacity of the bolt. It is found based on these. Okay, and then you have S, which is the spacing between, it is the vertical spacing between the bolts. And then you have to calculate the total shear, the ultimate shear acting on a bolt. Now, if you might have observed, if you might have listened to Dr. Al-Farabi's lecture, you might have seen that there are a few bolts which are more critical than the rest. Okay, for example, if you consider this force, the shear acting on, suppose there are like 10 bolts here. Due to direct shear, the shear on each bolt is equal. Because of Py, it will be equal. Because suppose you have 10 bolts, then the shear force on each bolt will be just Py over 10. Similarly, the shear force due to Px is simply Px over 10. But in the case of moment, the effect is different on different bolts, and we'll see in a problem how it is important. We'll see that some of them become more critical while the others don't become much critical. For example, in this case, I can just show you how it works. If you just take a look at, just zoom it in. For example, suppose there are a few bolts, and this is the resultant. Like these are the shears acting on each bolt. The vertical one is the one distributed from Py, and the horizontal one is one distributed because of Px. You see that on each bolt the arrangement is the same, because Px is the contribution from Px on each bolt is simply Px over 10, while the contribution from Py is simply Py over 10, and it's evenly distributed. But in the case of moment, it is a little different. The moment acts in this direction, you see. So the resultant of this one is acting like this. You can just use another color. This one is acting in this direction, and this one is acting in this direction. I think that color was very good. I'll use this color. The resultant is like this. Okay. Now, if you take a look at this bolt, the moment is acting in this direction, and the resultants look different. For example, they look something like this. Okay. Now, the moment acting on this at this point looks like this, and the resultants look something like this. And similarly, on this bolt, your resultants would look something like this. Okay. Now, if you take a look at this bolt, correspond to this bolt here, you see that this is acting downwards, and here this vertical component is also acting downwards, which means that it is adding up. While here you see that this is acting to the right, and again this is acting to the right, which means that the effects due to the direct as well as the moments are adding up. So this is like a critical bolt, because all the forces are being added up in the same direction, which makes it very critical. Now suppose you take a look at some bolt like this one, you see that as in the case of the first bolt, this is acting down and this is acting to the right. But here you see that the moment causes the resultant to go up, which actually cancels out some shear from here, and this acts to the left, which again cancels out shear from this bolt. So which means that this is less critical. This is the most critical. If you look at any other case, you'll see it's like a combination of both. Maybe one gets cancelled out, one gets removed. So you have to really sit and then draw this diagram, and then you see you have to analyze which one might be more critical. If you do a couple of problems, you can guess it by intuition, but this is something that you should know. I hope this idea is clear. Is it clear for everyone? You can just respond.
Yes.
Yeah, because this is very important. This idea is very important. Now, once that is done, you get the direct shear you get a direct shear by px over n, and the direct shear in y direction, this is because of the direct shear, y over n, and r, this is the shear due to the eccentric shear. So you have this particular equation which is basically a derivation from your torsion, because it's my over j, and then j is calculated like this. We'll discuss this one. And I have just missed out something here. This is supposed to be square. Okay, and this is supposed to be phi r and v. I don't know why I missed these. I will make the correction before uploading. Okay, so then based on the value of RVUV that you found, you can actually check it against the capacity of the bolt. If it is less than the capacity of the bolt, which means that your design is safe. Okay, I don't know if someone's mic is on. If you could just turn it off. Okay, thank you, because I'm wearing a headset, so it's disturbing. So but if you have any question, please feel free to turn on your mic and ask. Okay, you can interrupt me. Now we'll just do a problem before we go into eccentric tension. See, in this notes I have summarized all of these ideas which I just told now. This is how a problem is done. Now the first problem is to determine the required number of 3/4 inch bolt of type A325 in standard hole for the bracket plate shown below, assuming 4 vertical rows. See, you have been told to use 4 vertical rows. And the first type of connection is use bearing type connection, which threads included in shear plane. And then you have slip critical connection at limit strength, assuming class A surface. Limit strength assuming class A surface. You see that you can just analyze the problem. You see we have 2 brackets. This P, the load P, is distributed onto 2 of them. So we can just divide it by 2 to find the total force acting on each of the brackets. Okay, so the P ultimate is 1.2 times the dead load plus 1.6 times the live load. You get this value, and the PU per plate is just the half of it, because you have 2 plates. Okay, you might get a question with a single plate. So in that case, your P will be the PU itself. But since you have two plates here, you just have to design for one and put it for both. Okay.
Doctor, I can't determine whether it's one plate or two plates, right?
You will understand from the figure, right? Don't you understand
Yes.
from here? Yeah, but
Yeah,
you
it's
have
clear.
to identify. You have to identify.
Okay.
You have to identify whether it's one or two, because in this case it is just one plate, and then you have to divide it by two, and you have to just design for one plate because that will be the same for the other one as well.
Okay.
Okay. So now we have now the edge distance is calculated as BF over 2. I think, yeah, the shape is given to you. It's W14 by 132. So this edge distance is calculated from BF over 2 minus 5.5 over 2 minus 3. So the edge distance, that is the distance from the center of the bolt, center of the hole to the edge, is 1.6 inches. Okay.
Doctor,
Yep.
the two plates are holding what? The P is coming from where?
Yeah, it could be from another slab or a beam.
Okay, so the beam is above the two plates.
Yeah, it could be. Like I can just make that clear for you. If you want to, I'll just share my screen. Suppose you have, this is not very good. I'll just share my screen. Do you see my screen?
Yes.
That could, the idea is it could come from just see, this is one of the plate, and then this is like the plate on the other side. And then you have probably a small plate over here, support. Okay. And then this is the plate on which the P acts, and this might be connected to maybe some another beam or column, something that's coming from outside. We are not worried about the design of that. We're just worried about the load that is going to come from here.
Okay.
Okay, is it clear?
Yes.
Okay.
The edge distance, I don't quite get it.
Yeah, we'll go there now.
So, Doctor, always we will use plates to connect like columns and beams.
Yeah, you can. Yeah, you use this is a type of connection that is welded connection. This is how we connect probably some beam to this one. You need a connection. This is just one example of this.
Okay.
It need not necessarily be a plate. You can use an angle. One angle is connected to for probably the flange of the column, and the other leg is like a cantilever, and you can support another member on that. I mean, this is an example.
Okay.
You get the idea? Okay, it need not necessarily, it need not be plate always, it could be anything else. Okay, so he just asked how how to calculate the edge distance. You see, later on when we are calculating the capacity from bearing, we have a term called LC. LC is actually the distance from the edge of the bolt to the edge of the plate. This is LC. Okay, to calculate LC, first you need the edge distance. The edge distance is defined as the distance from the center of the hole to the end of the plate. Okay, so that from this
From the
figure,
manual,
for
right?
example, you have been given a yeah, LC has to be calculated. If it is given, it's fine, but otherwise in this problem you see that the plate is ends at the end of the flange of the W shape. Okay, so the
Okay.
width of the flange, this entire length is actually BF of the W shape, and this W shape is given to you. You subtract half of this because you have been given that there are 4 lines of poles and the spacing between them is given to you. This is like 3, this is 5.5, and this is 3. So when you want this particular distance, when you want this distance, which you call the edge distance, you have to separate, you have to find it by half of BF minus half of this minus 13, and the rest is the edge distance. I hope it is clear.
Yes, it's clear.
Okay, so to calculate the capacity of, yes,
The edge distance is the distance between the center of the bolts to the end of the blade, right?
it is the edge distance.
Okay.
Okay. So in design we saw earlier what is the limitation from in the manual, the edge distance. Okay. So now the shear, the capacity in shear of the bolt is calculated from phi r and v, where phi r and v equals phi f and v ab, and we are aware of this because we did. And here we have phi is equal to 0.75, FNV is 54. Okay, because it is, if you could just open the manual, go to page page 16.1, 120. 16.1, page 120. You have been given that threads included means it is A325N. Okay, so you get the value of FNV as 54, and AB is simply the diameter of the bolt. And what is this one? One is
Number
the
of
planes.
yes.
In this problem you have just one shear plane. Why?
2 plates, I guess.
Only in Y?
Yeah, only in Y, but what I'm meaning to say is there is only one shear plane, even though we have 2 plates. Why? Because
Because
you see, we are designing only half of it,
okay.
because this load is just half. It goes into PU by 2, PU by 2, and then if you look at this one alone, now you don't worry about the left part, because you're just worrying about this part. For example, in this you have just only one plane. You see, if you have a bolt here, it is only subjected to one plane of shear. Do you get the idea? You can just draw a small figure here. Suppose this is the flange and this is the plate. Okay, and you have a bolt here. Now the only critical area, the only shear critical area is just this one, because your the bolt is in shear only in one plane.
Yes.
That is this particular plane. Suppose we had more than one plates, for example, in the previous problems that we did, for example, you have like say,
Two
like,
plates.
yeah, suppose something like this. I'm sorry. Suppose you have something like one plate over here, one plate over here, and again another plate over here, and you have a bolt here. Now, how many shear planes
Two.
are there?
Two
Two
shear
shear
plates.
planes.
Two.
Here one shear plane and here one shear plane. But in this problem, we have only one shear plane. So we have just one here. And
Okay,
then,
because we already divided the PU.
yeah, we already divided it by this one, and you just have to design for
Okay.
this. It would be the same for that.
Okay.
Okay.
Yeah,
So
that's okay.
yeah. So RNB is again the calculation of uh, bearing strength. It is calculated from this equation. It is there in the manual. So if you remember, we had just uh, made it simpler by converting into this form, and then when you calculate the capacity, now the LC value is what? The LC value is edge distance minus half diameter of the bolt. So it is 1.6, the edge distance we calculated earlier, minus half times diameter, because LC is what? It is the distance from the edge of the hole to the edge of the plate. That is LC, and 2 times diameter of the bolt is 2 times 3 over 4. When you calculate this, you get the value of PRNB as 39.97 Kipberg bolt. Now this is the strength from bearing, and this is the strength from shear. Now which one is more critical? Shear. So this is your capacity in shear. So from here, the capacity of the bolt will be taken as this one, the least value. Now the next step is to approximate the number of bolts. To approximate the number of bolts, this is the equation that we discussed earlier. It is N equals square root of 6m over Rs. Okay. Now M is calculated as M is, just right here, M, your moment acting is how much? What is the total moment acting? Total moment M, say example MP is equal to how much, or just M is equal to how much? It's P is P times E. Okay, in this case you just have one force, you just have Py here. Okay, so what is the moment acting, total moment acting? It is P times 16. So what is the value of P per plate? It is 47. So this M value is the moment per vertical line. This is 47. That is the M required for this equation. Okay, so let's name it M dash if you would like to, because we used M earlier. Maybe you can say M dash, which means it is the moment per vertical line. So you have 47, that is the load, times 16, which is eccentricity. This is, I can just say, this is P, and this is eccentricity, and 4 is what? The number of vertical lines of
Vertical
force.
line.
Okay, so when you do this calculation, you get the value of M, and then R is the capacity of bolt. Now from the previous step, we calculate the capacity of the bolt based on shear, the shear controls, single shear controls. So the value of R is 17.89, and the spacing is 3 inches, which is given to you I think it is given to you from here. The spacing that you have chosen is 3 inch. So S, so when you substitute all these values, you get the value of N as 4 point. This is just an approximation, by the way. Okay, you might not get the correct answer in the first shot. You'll probably have to do one more iteration, for example, to get to the final answer. Now, for example, here you get N is equal to 4.58. This means 4.58 volts per vertical line. So suppose, so you can round it off to 5. So let's start off by trying 5 bolts per vertical line. So the arrangement would look something like this. There are 4 lines and each line has 5 bolts. So you have a total of 20 bolts. Okay. And this is the spacing that we were talking about. We had chosen it as 3 inches. Okay.
Doctor, we choose the S to be 3, right? We didn't calculate it.
Which one?
The S spacing.
Yeah, I think it must have been given in the question. Probably I missed it.
Okay. If it's given, I use it. But if I didn't given the
Yeah,
spacing,
if it is not given, you know, you have the spacing limitation, S minimum, S
okay.
maximum. Based on that, you can
Okay.
choose a value. Okay. So typically for your course, 3 can be chosen for anything. Like you can do the calculation just to show, but typically you can take 3 because 3 works for all cases.
Okay.
Okay, so here I have taken 3 inches, and then now this is the next important step, because here we need to calculate a term called the polar moment of inertia J, which is AB times square root, I mean the summation of xi square from 1 to 20, because there are 20 bolts, and summation of yi square from 1 to 20. I'll tell you what it is. So you see, what is the distance from the centroid? Let's talk about the bars, I mean the bolts, the horizontal bolt. Okay, you have 4 bolts separated by a distance of 6 from the centroid. Okay, and similarly at the bottom you have 8 bolts, I mean you have 4 bolts separated by distance. So you have a total of 8 bolts. You have a total of 8 bolts, this 4 and this 4, separated by a distance of 6 inches, right? And then you have 4 bolts here and 4 bolts here. So another 8 bolts separated by a distance of 3 inch. So based on this, you can calculate the value of sigma y square. So you have 8. This can be opened up as 8 times 3 square plus 8 times 6 square. So what does this 8 mean? There are 8 bolts separated by a distance of 6. So this is actually square, so which means there are 8 times 6 of them, 6 square, and 8 times 3 square. So you get a value of 360. Is it clear?
Doctor, the 3, I didn't get it from where 3.
Okay, I'll make it clear. I'll start from beginning. Okay. Now there are 2 terms that needs to be found. One is sigma x square and sigma y square. Okay. So this is actually, I can say it is like the sum of, you can say this is the sum of squares of bases of bolts. Sum of squares of distances of bolts. Okay. Now let's talk about the bolts in the vertical bolts, which is separated from the centroid, which is lying here. The centroid is over here. You're talking about each bolts measured in the x direction. Okay, in the x direction, if you take this layer, you have 1, 2, 3, 4, 5 bolts, or you can say 5 bolts separated at a distance of, how much is this? 3 plus 2.75, which is 5.75. 5.75. Okay, so if you want to calculate them separately, which means it's what? It's 5.75 square for this bolt, 5.75 square for this bolt, 5.75 square for this bolt, 5 square for this bolt, for each bolt. Even this one, if you look into the left, because it is symmetric, even these 5 bolts are separated at a distance of 5.75. So you have 10 bolts separated by a distance of 5.75. So you have 10 times 5 this is 5.75 square. Okay, so you are actually adding up just the distance of each bolt. So you have one bolt, so you can so that is separated by a distance of 5.75. So similarly, you have 10 bolts on either sides. Now similarly, you have another 10 bolts, like these 10 of them, separated by a distance of how much? Separated by a distance of 5.5, half of this, 5.5 by 2. Okay, so that is how this came into picture, because this is 5.5 by 2 the whole square, that is this distance, and you need to take it for each of the bolts. So you have 10 bolts, so it becomes 10 times. Now is this clear? When you do the math, you get this value. Is this clear now?
Yes, doctor.
Okay. Now similarly, you can do the same thing for the bolts in Y. You see, if I just rub this off, in Y you have 4 bolts at the top and 4 bolts at the bottom, separated by a distance of 6 inches. So you have 8 of them 8 of them together on either sides, separated by a distance of 6 inch. So what you do is, it's just 8 times the distance square. The distance is 6 square, so 8 times 6 square. And similarly, you have another 8 of them, these 4 and these 4, separated by a distance of 3 inches. So it is 8 times 3 square for these bolts, and 8 times 6 square for these bolts. So you get a total of 360 inch square. So sum of squares of these distances will turn out to be 766.2 inch square. Is this clear?
Okay, doctor. And the 5.5, is it given also, or I choose any value?
No, 5.5 is given.
Okay.
It is given in the problem. Okay. So now you have to calculate the indirect shear. What is the direct shear because of this force? If I ask you, what is the direct shear because of this force P? I have 20 bolts and P ultimate is 47. So what is the direct shear from the ultimate load? It is just 47 divided by 20. Is it clear? So direct shear can be calculated in that manner, but you need to calculate the value, the indirect shear. The value of indirect shear is calculated by Rx double prime. Here, if you look at, if you remember from the figure, I can just say that regarding the direct shear. This is the indirect shear. Before we go into indirect shear, I'll just revise the direct shear. You see the direct shear will be, let's say, Rx prime is how much? We have a force in Rx, I mean in the x direction. We don't have a force in x direction. This is 0. Okay. Now, but we do have a direct shear in y direction, which is equal to how much? Pu, which is actually 47, divided by what is the number of bolts that we calculated from here? The total number of bolts divided by n. So which is 47 divided by 20. Okay. Okay. Once this is found, we need to move. Once direct shear is found, we need to move into indirect shear. In indirect shear, again you have to find the value of Rx double prime and Ry double prime because of these moments. Okay. Now this moment is something that we know, which is just P times E. This Y is actually a variable. AB is just the area of the bolt, and J is the polar moment of inertia, which is this equation. Okay, so when you multiply, when you put J into this equation, this AB and this AB would cancel off. So basically what you're left with is just Ry or Rx double prime equals My over square root of x square and square root of y square. Okay, so your J can be calculated as this one. We just calculated this here. You can plug in that value here, because AB, it is also times AB. You can keep AB, but AB will get cancelled off in the next step. So you don't have to separately find AB. Your Rx is calculated based on My over J times E. So what is M? M is 47 times 16, which is the moment, times the Y value. Now this is where we discussed earlier, which is the critical bolt. Now you see that the moment is acting in this direction, and the ultimate this is how the moments would act. I mean, the resultant of the moments would look something like this, as we discussed earlier. This will look something like this. This will look something like this. These are the resultants, and this will look something like this, right? Now, because of the direct shear, which is acting in downward direction, let's use another color. Let's use let's use this one. Because of direct shear, there is vertical force on each of them. You remember, right? Which is just the total shear divided by the number of bolts you have on each of them. So which one is more critical? You have direct
I
shear
think
on each.
upper right.
Yes, upper right would be more critical. If you just take a look at it, you see that this moment has a component over here which actually adds up to give a higher value. Okay, but if you go here, for example, this will cancel off. Here again, what do you see? Even here it adds up, right? Even here it adds up. So these both are critical. It is a symmetric problem. So if you take this or this, it's going to be the same. So that's why the value of x that is chosen here is 5.75. That is the coordinate. You're just basically making this as the origin and calculating the coordinate of this point. This point is how much? The x equals to 5.75 and y equals 6. because you have identified that this point, this bolt is the most critical. You substitute the value of x, the value of y as 5.75 and the value of x as 6. Did I write it wrong? I think I have written it wrong. This is supposed to be, because if this is actually x and this is actually y, so this is supposed to be, from here you see that this is supposed to be y and this is supposed to be x. Okay, I will make the correction, something that I noticed now. So you get the values as shown here, Now you need to put, see the direct shear calculation as this earlier is done here. You see that the direct shear is only acting in the y direction. So now what you do is to calculate the ultimate shear because of all these. You can say it like UV, ultimate shear, RUV. You can say it is RUV is square root of Rx prime plus Rx double prime the whole square plus Ry prime plus Ry double prime the whole square. Now you know that Rx prime is 0 because you don't have direct shear in x-axis. This is 0, which means this term is not there. And you have Rx dash from previous calculation, you have Ry from here, and then you have Ry prime from previous calculation. When you sum it up, you get the value, the ultimate shear acting is just 9.98, which is much less than the capacity. So it is like a very conservative design. The number of bolts is high. Okay, so if you want a more economic design, you have to decrease the number of bolts because the strength is too than the load acting. So for that case, what I do here is, earlier problem we had 5 number of bolts. Now I decrease it to 4 number of bolts per vertical line. So the arrangement would look like something like this. Okay. So then I repeat whatever I have done there. I find the value of sigma x square, sigma y square. I find the indirect shears, and then I find the direct shear here, and then the ultimate shear is calculated. And you see that when you choose 4 number of bolts per vertical line, it is closer to 17.9, which makes it a more economic design. So these are some of the checks. This can be done in the beginning as well. I've just done it at the end. It can be done also in the beginning, as we had discussed in the steps, that this arrangement can be done in the beginning. You see that the spacing calculation has been done later on. This is 2.25. The spacing maximum is 6. What we had chosen was 3. But if it's given the problem, I don't think you'll have to check. You can just skip that. And then finally you do the detailing. After you have calculated the number of bolts, you can just do draw a diagram with all the detailing, that you have 4 number of bolts per vertical line, and then you have taken the separation, and this is the edge distance, and you can just draw a diagram showing all the details. Okay, now in bolted connection subjected to eccentric shear, you don't have to check the block shear. Okay, block shear case will not be critical, so you don't have to check block shear. Block shear is only required when there is direct tension. Okay, not direct tension, direct shear. When there is direct shear, you have to do check for block shear, but when it is direct eccentric shear, you don't have to, okay, because your block shear is not going to control. If you take a look at this, for example, you have like a few bolts here, you subject it to shear, you see that this could separate in a few modes that we discussed earlier. But when in the case of indirect shear, it is like a twisting moment, and then there is no clear plane of failure for the shear, so it is less critical compared to a direct shear problem. So you don't have to really check this. So I've just written it as a note here. So now in the same problem, we also have to calculate the capacity if you are using a slip critical type of connection. For example, in this problem, we have taken A325C. You know from before that the value of PRN is calculated based on the equation in the manual. You know these values are, this is taken as 0.3 because it is class A surface. This is from the manual. This is from the manual. The pre-tension is also from the manual for this type of bolt A325SC. The value is 28 kips, and then you have shear plane as we discussed earlier. The calculate and the capacity. You see the capacity is smaller in the case of uh, a slip critical, and then you can find the approximate number of bolts based on the same equation we discussed earlier. You require more number of bolts. For example, here you need 6.3. Earlier in the previous, we saw that when we had taken a higher value, it was very conservative. So I started off by trying something smaller, 6 bolts per line. I substituted the values. I did it the same way as we did before, and then I found ry dash as before, and then rx dash, and the direct shear, and then I substitute into this equation. I see that the value, the shear acting, the ultimate shear acting is just 7.71, which is slightly, which is less than 9.4 the capacity. So therefore, if you're going for a slip critical type of connection, you have to use a total of, number of bolts per line, so a total of 24 bolts. So this is the design for slip critical type of connection. You have a question in this part?
So, Doctor, both slip critical and bearing, we don't have to check for the block shear if it's indirect.
Yeah, no. Block shear is only required in the case of bearing type of connection subjected to direct shear.
Okay.
Even you don't need to check for slip critical.
Okay.
Only for bearing type connection, because slip critical does not, because the whole area is in contact with each other. There is no specific shear failure planes in that, so you don't have to really do that for slip critical type of connection.
Okay.
Okay, so any questions in this one? Anyone else? Any question? Because now we have to move into eccentric tension. Okay, now let's move into eccentric tension. As you may have guessed, I'm sorry. Excuse me. Okay, now let's move into eccentric tension, which is comparatively easier. Are you seeing the slide?
Yes, sir.
Yes. Okay. So you see that you have W shape, and then you have something like a WT connected to this, and then you have a tension acting which is not direct, which is an indirect tension. Okay. So what do you think is the next step? How do you solve this problem? You have to transfer. Yeah, you have to transfer your indirect tension into a direct tension, and then you'll have a moment acting, right? So you see that your eccentric tension can be split up into a direct tension plus a moment. Okay, this T times E, this moment is actually T is E. So you calculate tension because of, sorry, you calculate tension because of the, suppose you have say 4 bolts here. Suppose you have 4 bolts. What will be the tension on each of the bolt? It will be just T divided by 4, right? But in the case of moment, it is different. Because it is moment, you see that only these bolts, that is the bolts above the centroid, will be in tension. You go below, the bolts don't really act because of this moment, because the plates are just pressing on each other. You get the idea? You have any question?
Okay, Doctor. Clear.
Yeah, I'll just make this clear. Yeah, suppose this is like a W shape. Okay, and then you have say a WT here. And there is a direct tension. This direct tension, suppose there are like say 4 bolts on each. There are 2 lines, so we have a total of 8 bolts. Each bolt will be subjected to a value of T over, each bolt will be subjected to a tension of T over 8. Okay, but suppose this is not the case. Suppose suppose this is a direct, suppose you're talking about moment, the case would be different, because you see, because of a moment, say for example, you see that above the neutral axis, these both are in tension, and both are at different levels of tension. For example, this is subjected to a lesser tension compared to this one, because you see there is a moment, and then you see that this is subjected to less tension, this is subjected to higher tension. But in the case of the bolts below the neutral axis, this moment does not really act, because these plates, the flange of the W shape and the flange of the uh, WT shape and the flange of the W shape, they just press on each other without actually causing any forces in the bolt. Okay, so if you already have a tension, this would not really act. Okay, this would really subtract the effect of the tension that is already acting in that. Suppose you have tension, suppose you have an equal tension acting on it, say like for example 10 kips because of the direct shear, and then suppose because of the indirect shear you have say like, I don't know, say like 8 here, and then like, I don't know, maybe like 8 here. Okay, so what will be the resultant? Like this is plus, this is like minus, so your ultimate would be like 18 and what, 2. Okay, suppose your moment is much higher than that. Suppose you have a tension from direct shear of say 10, and suppose you have something higher, suppose you have something like 12 here and something like 12 here. When you add this up, you're supposed to get what, 22 over here, and how much here, minus 2 over here. This minus will not work in the case of W shape. It will be just like 0 over here. okay, because the plates just hit each other, they don't really try to compress the bolt. So let me just open the slide. So what happens is you have a direct shear as well as a moment, as we discussed. Okay. Now the design steps are quite easy. You have to design the layout of the bolts. You have to calculate the capacity of the bolt in tension. This is simply phi r and t. What is phi r and t? Phi r and t is equals phi r and v r and t phi f and t times ab. Something that we know. And then for the moment you have to calculate the number of bolts required based on this equation and choose which is more critical, and then you have to calculate the capacity based on two of these. The first one is the capacity, I mean from the direct tension, I mean this is not capacity, this is the ultimate load, RT prime, which is TU over N, and RT double prime, which is MY over sigma y I square. I'll just do a problem, this thing will be clear to you, and then you add this up. This ultimate the ultimate tension should be less than the capacity phi r and t. That would be the final. So let's do a problem. I think the idea will be much clearer after we do a problem. Okay. Now you've been given determine the number of 7 or 8-inch diameter bolts for the connection shown. If T ultimate is given to you 95 kips, your eccentricity is given as 4 inch, the vertical space is to be taken as 3 inches. Use LRFT specification. Assume 2 lines of bolts of A325. So this is how the problem looks like. The layout of the bolt is actually calculated based on the spacing as well as the edge distance, which is available in the manual. I mean, we have gone through this. Just to check, because the spacing has already been given, so just to make sure that it is within the limits, you can just check the spacing. Now the capacity of the bolt based on tensile strength, so phi r n v is phi f n a b, which is phi f n t a b. This is from the manual. F n t is taken, it is from the same page that we discussed, we showed earlier, I think page 16.120, where we found FNV. You find FN as 90 ksi, plug in all the values, you find the capacity of the bolt in tension as 40.5. So the number of bolts based on direct tension can be calculated by simply dividing the total tension over the capacity of each bolt. So you get 2.34 bolts, but this is not right. You have to also check the bolts required based on the moment as well, because if you did not have a moment, this is, if you had a direct shear problem, this would be like the final answer. But since there is a moment as well, we need to calculate the number of bolts, we need to estimate the number of bolts based on this equation, and then check with the strength of the bolt. Now we told that M here is the moment, that is the tensile, the force times the eccentricity, and we have per line, so we have 2 lines here, so therefore we use 2 in the denominator. So you have a moment of 190 kip in per line. The R in this equation is the capacity. The capacity is phi R N T, which is 40.6. We already calculated earlier. The spacing is given as 3 inch. You can go ahead with 3 inch. Substitute all the values. You get the number of bolts as 3.06 bolts per vertical line. These many bolts, the value of n that you get in this equation from this equation is number of bolts per vertical line. So if you start off with this approximate value, you have 3 bolts vertical line. So you have a total of 6 bolts. 1, 2, 3, 1, 2, 3, 4, 5, 6. You have 6 bolts in this diagram. Okay. And now to calculate the ultimate tension, you have to calculate these two quantities, which is RT dash and RT double dash. This is from the direct. This is from the direct tension, and this is from the indirect tension, or the eccentric tension, you can say. From the eccentric tension. So from direct tension, you found the value as Tu over n, which is 95 divided total of 6 number of bolts. So you get 15.83 kip per bolt, and RT double dash is My over sigma yi square. So your My is M is basically T times E, and you know the maximum tension because of the moment will be in this layer of bolts, the topmost layer of bolts. So the distance from the centroid is 3 inch. You take this value as 3 inch. Yi square, it is actually the sum of pairs of distances of bolts measured from the centroid. So you have 4 bolts, each separated from the centroid by a distance of 3. So 4 times 3 square. You get a value of 31.66 kip per bolt. Add them up, so you get a value of 47.49, which is higher than phi RNT, because phi RNT was calculated as 40.6. This is much higher, so we need to increase the number of bolts. So let's increase by 2, take 4 number of bolts per vertical line. So your RT dash calculated as 0.75 is 95 divided by 4 times 2, that is 4 number of bolts in line, and RT dash is y over yi square. To have m, this is m, and your y is in the topmost bolt distance of 1.5, because it is 3 and 1.5 divided by 4. We have 4 screws, 4 bolts separated by a distance of 1.5, so times 1.5, and then we have 4 bolts separated by a distance of 4.5. So you have 4 times 4.5. So when you substitute all these values, you get a value of 19 kip per bolt. Add them up, so you get 30.875 kip per bolt, which is less than phi RNT, that is 40.5. So this is how you calculate. So finally you can say that use 4 number of bolts per vertical line, or total of 8 bolts, and then you can just have a detailing a diagram showing the spacing and everything. This is the end of the lecture. You have any question for this, or the other you can ask now?
I have a question, sir.